I continue and finish today section 4.2 on logarithmic functions and their graphs. More graphing. Last time we took a look specifically at what logarithmic functions were, and today we're going to take a look at the graphs. So many graphs in this course. Okay, so we're going to graph some logarithmic functions, but before we do that, I would like to quickly graph the same thing we did last time, which was y equals 2 to the x power. So this is an exponential function, and when we graph that, we could quickly do a table of values, x and y. And one thing you remember is for these exponential functions, it always goes to the point 0, 1, because anything to the 0 power equals 1. And let's just get a couple other points here. 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8. Okay, so we have the point 0, 1, 1, 2, 2, 4, 4, 8, 3, 8. And you'll remember, hopefully, that the way these exponential functions look is that they have a horizontal asymptote at the x-axis, and the graph gets closer and closer and closer to this asymptote but never touches it, comes up through the point 0, 1, and then depending on what the base is, it'll go up at a different rate. So this graph right here is y equals 2x. Y equals 2 to the x power. Alright, why did I graph that? Because the inverse is, well, remember how we get the inverse? We switch the x and the y. So the inverse is x equals 2 to the y power, and then we would try to isolate the y, and we can't do that, except now we can, because we have learned from last day that x equals 2 to the y power, what I have written here. There's another way of writing that, and the other way to write that is that y equals the base 2, this is a base here, 2, right? So the base 2 log base 2 of x equals y. So now what we're going to do is we're going to graph this. Now remember, these are inverses of each other, so when I graph this, you should not be surprised by the points, and you should also not be surprised by the graph if you remember about inverses. If you don't, you'll soon remember. Okay, so let's graph this. Now it actually turns out that when you graph logarithmic functions, it's actually easier if you graph, or when you're trying to find points, if you use this form of it here. At least for me, I find it easier. And actually, this is one case where it's not easier to pick values for x, it's easier to pick values for y. So for example, if I pick the y value of 0, I get 2 to the 0 power, which is 1. If I pick the y value of 1, I get 2 to the first power, which is 2. If I put 2 here, I get 2 squared, which is 4. And if I put 3 here, I get 2 to the third power, which is 8. Now take a look over here, and what do you notice? And hopefully you remember, all the points are just opposite from each other. They're flipped. The points are, I don't know the best way to say it, reversed maybe? Instead of having 0, 1, we have 1, 0. Instead of 1, 2, we have 2, 1. And remember we said that when we have inverses, that's exactly what happens with the inverses. So let's graph those points. What the heck, I'll do it in green. So we have 1, 0. We have 2, 1, we have 4, 2, and we have 8, 3. Now, if you remember about inverses, you probably know already what this is going to look like. But let's say you don't remember. Let's try some smaller value. Let's try negative 1 in the y value. 2 to the negative 1, that's a flipping negative, so it flips over, you get 1/2. Let's try negative 2. 2 to the negative 2, that flip it over and then square, you get 1/4. Okay, that should be enough. So 1/2 negative 1 is 1 point, 1/2 negative 1, and the last point, there we go, and the last point was 1/4 negative 2. 1/4 negative 2. Do you see what's happening here? You have got, because as you get bigger and bigger negatives, this is just going to keep getting closer and closer to the y-axis this time. Whoops, that should be very close to the y-axis. Should come up like this and go through like that. Now, this graph is, we could write either one of these two. I'll write this way, y equals log base 2 of x. What do you notice about these two graphs? Do you remember something about these? If they're inverse graphs, they should be, and these are, reflections of each other over the line y equals x. So there's a line that goes through the origin from corner to corner more or less, and the equation of that line is y equals x. And these two graphs are inverse of each other, which means that they're just reflections of each other over that line right there. Okay? So hopefully remember that for about inverses. All right, let's do another one. This one we had a base that's greater than 1. Let's do a base that's smaller than 1, but it has to be bigger than 0. So let's do y equals... Oh, by the way, this logarithmic function here is called an increasing function in this case. Okay, let's do y equals 1/2 to the x power. So again, this is the exponential function. X, y, 0, 1, 2. 1/2 to the 0 power is 1. 1/2 to the first power is a half. 1/2 squared is a quarter. It'd be nice if we got some bigger numbers. So let's do a negative x value, because that'll flip it over and you get 2. And if you put -2 in there, you flip it, you get 4. So let's graph that. Again, it always goes through 0, 1. And then we have 1, 1/2. 2, 1/4. So again, it's coming down to that horizontal asymptote. -1, 2, -2, 4. You can probably guess, or you can figure out. It goes through -3, 8. We talked about this last time. It's really just a reflection of this black graph here. It's a reflection over the y-axis. So it looks like this. Okay. Now, if this is y equals 1/2 to the x power. Again, the inverse is, for the inverse, we switch the x and the y, so we get x equals 1/2 to the y power. Or another way you could write that is y equals the base 1/2 log of x. And this time we know what's going to happen to the points, right? We've already talked about this. They're just going to switch. So where we had 0, 1, it's going to go to 1, 0. Where we had 1, 1/2, it's going to go 1/2 to 1. Where we had 2 1/4, it's going to go to 1/4, 2. What other points did we have? We had -1, 2, so it's going to go to 2, -1. We had -2, 4, so it's going to go to 4, -2. And we also put up there somewhere -3, 8, so 8, -3. And it looks something like this. We have that vertical asymptote at the y-axis. Goes something like this. And again, if I was to draw that y equals x line, you will see that it's a perfect reflection over that line. In this case, this is a decreasing function. All right, so let's summarize this in this little table. What we had was two functions. We're going to summarize this first case here, this graph here. The first function we had was y equals 2 to the x power, and then the inverse function was y equals the base 2 log of x. Or the other way you could write that, remember, you could also write that as x equals 2 to the y power. The domain in the first case, so in this black line, what's the domain? Stretches forever in this direction, also ends up going forever in this direction slowly. So the domain is all real numbers. What's the range in this case? Well, it never reaches, the y never reaches 0, so all the y values are greater than 0. What's the x-intercept in this black case here? Never touches the x-axis. There is none. How about the y-intercept in that black case? Yeah, there is a y-intercept. Remember, it always goes to that point at 0, 1. And the asymptote, we said, was the x-axis. Okay, let's compare that to the green graph. What's the domain of the green graph? The green graph, all the x's are bigger than 0. It never goes below into the negatives. So the domain is x is greater than 0. what's the range? Well, it goes down forever and also goes up eventually forever. So the y is element of all reals. See what's happening here? It's all switched, right? X is the element of all reals, y is an element of all reals. Y is greater than 0, x is greater than 0. Guess what's going to happen here? If we look for the x-intercept of this green line, it goes through 1, 0. Remember, there's a y-intercept at 0, 1. Now there's an x-intercept at 1, 0. That point just switches. And guess what? Without even looking, you probably can tell by looking at the table, there's going to be no y-intercept. Yeah, that's right. There's no y-intercept. And finally, the asymptote, it's not going to be at the x-axis. It's going to be at the y-axis. Okay, so once you get the exponential function down, you can use that to help you with the logarithmic functions because they're just inverses of each other. All right, a few points about that. Logarithmic graphs, first of all, what we're talking about with logarithmic graphs is graphs like f of x or y equals the base b log of x. And something I didn't stress last time, but it's very important, is that in all these graphs, all these functions, x has to be greater than 0, right? We've already seen that in our domain, the x is greater than 0, so that's not so shocking. But what is more, I don't know, non-intuitive is that b, the base, has to be greater than 0, and b, the base, also cannot equal 1. Now, I don't know if I want to get into that now. It could take me a little time to explain that. A couple more points about logarithmic graphs. They go through the point 1, 0. We saw that. They also go through the point b1. Remember, the exponential functions or exponential graphs went through 0, 1, and 1b, and now we just reverse it for the logarithmic graph. And the vertical asymptotes at the y-axis. Remember, with the exponential function, it went through the x-axis. Everything's reversed. Okay, now we're going to graph something. We're going to graph this big thing here. In order to graph this, why don't we start by graphing the kind of mother function of this, which is just y equals log 3x, the base 3 log of x. So in order to graph that, this is the same thing as x equals 3 to the y power. And we can quickly get some points. If our y is 0, x will be 1. If our y is 1, x will be 3. If our y is 2, x will be 9. Can't go any higher because x's won't fit. How about we put one negative in there too? If y is negative 1, x is 1/3. So 1, 0, 3, 1, 9, 2, 1/3, negative 1. And hopefully that's enough to remind you, oh yeah, we have an asymptote on the y-axis. It's going to get closer and closer and closer. It's going to go through 1, 0, and it's going to go like that. Now, is that this graph here? No, but we can use that now because this graph is just going to be the green graph transformed. How is it transformed? Well, be careful. The first thing you have to do is you have to switch this. It's not in the correct form. Y equals log base 3. Now, you want this x to just have a coefficient of 1, so you're going to have to factor out the negative, as we've done many times in this course, and you're left with x take away 2 plus 1. This is now in the correct form. Now we can take a look at our transformations. Now, let's take a look first at the vertical transformations. What numbers in here impact the y values? The only one that impacts the y values is this plus 1. And what does it do to all the y values? It adds 1 to them. So let's do that first. Let's just add 1 to all these y values. 1, 2, 3, 0. Okay, now we have two transformations in the horizontal direction. We have this negative, which is a reflection over the y-axis. What that does to all the x values here is it makes them negative. And then you have to have this. You have this minus 2, which moves it 2 to the right. You have to add 2 on. So we make this negative, negative 1, and add 2. You end it with 1. Make this negative, negative 3, and add 2. You end it with negative 1. Make this negative, negative 9, and add 2, negative 7. And make this negative, negative 1/3, and add 2, you get 1 2/3. So there's some points that'll work for this new graph. Oh, by the way, what will be the asymptote of this graph here? Well, the asymptote is usually at x equals 0, and horizontally what we've done is we've made it negative. Well, that's not going to impact 0. Making 0 negative is still 0. and then adding 2. So our asymptote is no longer at x equals 0, it's at x equals 2. So why don't we draw that in right away? So there's the asymptote. And now let's graph these points. 1, 1, negative 1, 2, negative 7, 3, and 1 and 2/3, 0, so right around there. And we know it's going to get closer and closer to this asymptote, come up through this point, through this point, through this point, and through this point. There's the graph there. This is your graph right there. Now, is it what we'd expected? This, if we look here, this negative makes a reflection over the y-axis. Yeah, that's what's happened to the green one. It's reflected over the y-axis, so instead of facing out to the right, it faces out to the left, and then we want to move it 2 to the right and 1 up. And yeah, it looks about right. Moved it 2. Yeah, I feel good about that graph. Okay, next, determine the domain of the following logarithmic functions. Well, remember, this is where you have to use this stuff up here. The argument, remember this this amount right here is called the argument. We've said that that amount has to be greater than 0. So in this case, we need to have 2x plus 1 is greater than 0. That's quick to solve. 2x is greater than negative 1. X is greater than negative 1/2. Oh, that's not too bad. Okay, the base, there's two things about that. The base, we said, has to also be greater than 0, but the base also cannot equal 1. So let's solve both of those. X is greater than negative 3. X cannot equal, take away 3, negative 2. So x, it has to be greater than negative 3, but it can't equal negative 2. So we have to include both of those things in it. Okay, the last one, let's use a different color. There's two things in here. First of all, the base, 6 minus x, has to be greater than 0, and it also has to be not equal to 1. And then the argument, x minus 3, also has to be greater than 0. So let's solve this. Take away 6 from both sides, you get negative x is greater than negative 6. Divide both sides by negative 1. Oh, that's going to flip the sign around. You get x is less than 6. Subtract 6, you get negative x is not equal to negative 5. Divide them both by negative 1, x is not equal to 5. Add 3 over here, x is greater than 3. So let's think about this for a second. If we put on a number line, x is less than 6, so it's an open circle at 6. X cannot equal 5, so that's also an open circle at 5. It can equal 5. And x is greater than 3, open circle at 3. So it looks something like this. It can be from here up to 5, but not 5. And it can be from there up to 6, but not 5 as well. So probably the best way to write that would be that 3 is less than x is less than 6. In other words, it has to be between here. And then also add on that x cannot equal 5. I think that's the best way to do that. Okay, determine the inverse of the following. To find inverses, we switch f of x to y. Then we replace our y's with x's and our x's with y's. Now remember, if we're doing the inverse, this is an exponential function. The inverse is going to have what in it? It's going to have a logarithm in it. So let's turn this into logarithmic form here. So that would be log base, what's the base here? The base is 3, log base 3. The argument is x equals the exponent, which is y minus 1. And now what we want to do is we want to get that y by itself. That's no problem, just move the 1 over. So we get y equals the base 3 log of x plus 1 when we move that over. The last step is to switch that y into inverse f of x, sorry, equals the base 3 log of x plus 1. Okay, last one. This is a logarithmic function, so when we take the inverse, you should get a exponential function. So change this to y equals 3 minus log x plus 4. Where you see y, put x. Where I see x, I put y. We need to isolate the logarithm. Let's move it over here to make it positive. So we get logarithm y plus 4 equals 3. Let's move the x over, minus x. So we've isolated the logarithm now. So now we can change this in exponential form. What's the base of this logarithm? I don't see a base. That means it's a common logarithm with a base of 10 raised to the exponent 3 minus x equals the argument y plus 4. Got to get that y by itself, so let's make it y equals 10 to the 3 minus x. Bring the 4 over, it becomes minus 4. Last step, change the y into inverse f of x equals 10 to the 3 minus x minus 4. And we are done. Hope you're enjoying logarithms. We got quite a few more days of them to go.